we can now look at for a moment at only reversible cycles. For a reversible cycle, we see that del q by t integral is equal to 0. Cyclic integral of this is equal to 0. So, we see that the cyclic integral here now is being 0, and we can see what happens when we look at this for different cycles between the same points, say 1 and 2. So, let us say I have a cycle which is some A and B. I have another cycle which is some A and C, going like this in A, coming back in C. I have another one cycle going in A, coming back in B. So, for the cycle 1 A 2 B1, what I see is this cyclic integral is a reversible cycle. I am only looking at reversible cycles. Cyclic integral del q by t is equal to 0, which means that any heat I transfer in A if I was integral of this should be equal to 0. If I was to look at this other cycle 1 A to 2 back by C to 1, I again see that this is true. This must also be true. So, what I can see from this is okay, this is actually integral from 1 to 2 on QA. I can expand these. This is from integral from 2 to 1 on QB. This is 1 to 2 on A. This is from 2 to 1 on QC. So, I have just taken some arbitrary cycles. So, if I subtract these, what I see is essentially I see that this integral of del q by t on this path going between the same 2 points is equal to that going on some other path between the same 2 points. And if I was to take some arbitrary number of paths, I can show that on any path between the same initial point and the final point, the integral of del q by t is the same. I am only looking at reversible paths. On any reversible process or reversible path, I can show that in this fashion del q by t integral is the same. So, when we are looking at first law, we had, if you remember, a similar thing. So, the first law for a cyclic process was cyclic integral of del q, cyclic integral of del w. But then we saw that if you do not complete the cycle, if you just go from some point 1 to some point 2, we saw that if you take del q minus del w, it comes to some difference in some value, and that difference does not depend on which path you go in, as long as you have the same initial and the same final point. So, we saw that that is a property because it is not changing depending on which path we go, and we called it as some dE. So, in the same fashion, what we see is that if I go in the full cycle, in a reversible cycle, then the cyclic integral is 0. If I do not complete the full cycle, if I just go from some point 1 to some point 2, or in this case from point 2 to some point 1, as long as I go on a reversible path, it does not matter which path I go on, this difference is the same, this del q by t is the same. So, therefore, this del q by t must be some change in some property Over here we wrote this del q minus del w as some change in some property as dE. This must also be some change in some property. We are usually calling that property as some s. So, we can write this as some ds, or we can integrate this and say delta s is essentially the integral of some del q by t for a reversible process. All of these are for reversible processes. So, I can just emphasize that by writing this REV over here, saying it is reversible. So, what we see is, even though in the first law we saw that del q is a path function, del w is a path function, but the difference is a state function or a property which we call as energy. Over here del q is a path function, t is a state function or a property, del q by t is a property or a state function. When in math you would see that you have what are called integrating factors which convert inexact differentials into exact differentials. So, over here for example, this 1 by t is an integrating factor which is converting an inexact function del q to an exact function ds. So, that is something which we see. So, we got a property from first law which we call as energy. Similarly, we are getting a property from the second law which we are now calling as entropy. This entropy can be defined in many ways in different fields. It is also defined in different ways in, for example, statistical thermodynamics. In the classical thermodynamics we are looking at, essentially it is the ratio of the heat transfer to the temperature at which it was transferred. So, for the moment we will stick to this, we will see more versions of this as we go ahead. What we see over here is that we have defined this value only for a reversible process. In the case of an irreversible process, we do not have a way of finding out the delta S for an irreversible process directly, because in the case of an irreversible process, one of the things is we do not even know the process correctly, because we do not know what is happening. In the reversible process, we are in equilibrium, so we can plot all the points of the process correctly, we can find out this. But what we see is that entropy is a state function. So, that is an interesting thing. So, for example, on a PV diagram, if I have some point 1 here and some point, let us say some point 2 here, let us say I go on a reversible process from 1 to 2, then I can find some way of calculating delta S, because that is equal to del q by t, the integral of this, because this is a reversible process. So, I can find this. Supposing I go in some irreversible process, we usually draw them by dotted lines, because it means that we do not know the exact states. So, I cannot draw it on a graph. See, for drawing a graph I need to know all the points. If you do not tell me the points, I cannot draw. So, I do not know the points, I cannot draw this. So, we draw it by some dashed lines. More commonly we just draw dashed lines in some arbitrary shape. We do not necessarily draw it, we do not know the shape, it is some arbitrary shape. We draw it as dashed lines to emphasize that we do not know that shape. So, you should not find out areas under this curve or anything like that, because we do not know the shape of this curve. But if I go from this point 1 to 2, I cannot use this formula on the path 1 to 2. Over here this del q requires a path, because it is a path function. So, this is along this path A, for example. For finding out between this 1 and 2 on A, I can find out. If I want to find out on this path B, I do not know del q on path B, because I do not know the path B. So, I cannot use this formula. But what I do know is, if I reach the same state 2 finally, then the change in entropy between 2 and 1 should not matter on how I got from 1 to 2, because entropy is a state function. So, what we see is that S is a state function or property, that is what we proved over here. So, even though I cannot find out this integral for an irreversible process because I do not know the paths for del q. If I can know the initial and final states of a process, I can find an equivalent reversible path between those 2 points, calculate the change in entropy, and that should be the same for any process between those 2 points. So, this delta S for B will still be equal to delta S reversible as calculated for A. That is something which we can say, but delta S for B is not equal to delta Q B by T. This is not correct, but it is equal to whatever I can calculate on the reversible path A. So, that is essentially what we can see. This is not correct because we saw that according to the Clausius's inequality, this is an irreversible process. For irreversible processes, we do not have an equality here. We have cyclic integral of del q by T is less than 0. That less than 0 does not give us any useful way of finding out how much this is. It only tells us this value is greater than something. It does not tell us what the value is. But if I find, if I have any reversible path between any 2 points which I want to find out the difference in entropy for, then I can find out on that reversible path what is the difference, and any other irreversible process. For example, if I have some other irreversible process between the same 2 points, the change in entropy is the same as for this reversible process 1 to 2. So, that is how we will find out the difference in entropy for different processes. Now, we can also look at a few other things. So, this entropy is essentially what we are calling as S. So, it has units of heat transferred divided by temperature. So, it has units of say joule per Kelvin. In a similar fashion to which we are defining specific properties, we can define small s, which is specific entropy, which we would get by finding out Q reversible by T instead of capital Q a small q, or essentially capital Q reversible divided by mass into temperature for a process. For example, for 1Q2, if this was, we can only write this if it was a constant temperature process, or more generally del Q reversible integral, and this would have units of essentially joule per kg Kelvin, which we see are similar units to that of the specific heat, or for example the universal gas constant, not universal, the specific gas constant, and so on. So, that is something which we see. In the context of this, it is also useful to look at the third law. Of thermodynamics. Again, there are various statements of this to take into account some very specific things, but for the purpose of our systems and our course, I think one paraphrasing of this law could be that for pure substances, if we reach a temperature of absolute 0, the entropy of the substance would be 0. Well, the more correct way to see would be that it tends to some constant value, but anyway, for our purpose we will say that at absolute 0, we are looking at pure substances, we will say that the entropy is essentially 0. So, that is the third law, which gives us some reference for calculating entropy, because all of these formulae we have, it tells us del q by T. So, it only tells us what is the change in entropy. So, which means we need a reference. So, for pure substances of the kind we are dealing with, we will assume that at absolute 0 the value is 0. So, for any other temperature we can see how much heat we need to transfer to get to that temperature and use that to calculate how much the entropy changes by. So, that is also something which we see. So, what we can also see is how to calculate changes in entropy for various substances, and in the context of this we can see how to combine some equations which we have. So, we will look at the first law. We were writing it as, say for example, dE is del q minus del w, which gives us del q is dE plus del w. Let us look at simple compressible substances, which essentially means that we are not looking at, say, electrical and magnetic energy and so on. Our system is static, so changes in kinetic and potential energy of the system are not important. So, which is an assumption we have been making a lot of times. So, then this energy, which is essentially internal energy plus kinetic energy plus potential energy plus other stuff, none of those are relevant. So, only the internal energy is relevant, and we get this kind of an expression. So, if we now look at a system undergoing a reversible process, then for a reversible process we can write del q as TdS, because what we just saw just a little while ago is that ds is del q by T, which is essentially what we saw in the definition of entropy. I should write capital S over here, is capital Q, so it's capital S. So, we saw ds is capital Q by T. So, I can write del Q as essentially T into ds, and this is du. If I have a system where I have, for example, something expanding, then del W, this is a simple compressible substance, there is no shaft work, there is no other kinds of work. So, this is essentially PdV is what we have been saying so far. So, we have this kind of an expression. So, we have this expression. I can divide everything by mass, then I get essentially Td small s is du plus Pd small v, which is what we call as the Gibbs relations. So, this is one of the Gibbs relations. I can also get another expression. So, I know that enthalpy is defined as U plus PV, specific enthalpy is defined as U plus PV. So, this means dH is du plus PdV plus VdP. So, this du plus PdV is essentially dH minus VdP. So, if I substitute that into this equation, I get another equation which says TdH is equal to dH minus VdP. So, both these together are what are called as the Gibbs relations, and they can be used to find out changes in entropy. This conversion from del Q to TdS is only true for a reversible process. This is true for any process, this is true for any process. Conversion from del Q to TdS is true only for a reversible process. Conversion from del W to PdV is only true for a reversible process. But once we have these expressions, this is a relation between properties, and properties are properties for any process because they are state functions, they do not depend on the process. So, even though we got this equation by assuming reversible processes, once we are dealing with changes in properties, we saw that it does not matter which process we used to get there, as long as the starting point and the ending point is the same, relations between properties are the same. So, for example, if I have a process like this, I go from 1 to some 2, let us say this is a reversible process, let us say I want to find out change in temperature is simply T2 minus T1. If I have an irreversible process, I start at some point 1, I do not know how the process is, I go all over the place, I come back to point 2. Once I have reached point 2, change in temperature is still T2 minus T1. It does not matter what process I took to come there. So, what we see is these are property relations, and once I have the initial and final state the same, I can use this relation irrespective of how I got there. So, we can use this even for irreversible processes as long as we know the initial and the final state. Now, we can use these to find out some changes in entropy for different processes. So, for example, let us say I have like say solid or liquid. In a solid or liquid, I can use this first relation for example. So, I have TdS is equal to du plus PdV. In a solid or liquid, specific volume is very small because the density is large. Changes in specific volume are even smaller. So, this term is approximately equal to 0. So, I have TdS is equal to du, that is equal to Cv dt, because I am looking at small u, so the mass is not there. So, if I wanted to find out ds, that is essentially Cv dt by t, or if I want to find out delta S, S2 minus S1, I can integrate this. If I assume Cv to be a constant, then I get Cv times ln of the final by the initial temperature. So, if I have a solid or a liquid which is being heated and there is change in temperature, I can use this to find out what is the change in entropy. So, that is something I can do. If for example, there was no change in temperature, which is what would happen if there is for example change in phase, then instead of the du being Cv dt, I would have the du as essentially the change due to the latent heat, and I could divide that by the temperature, saturation temperature at which it is happening, and find out ds. So, I could also do that. Now, I can also find out the same kind of a change in entropy for an ideal gas. So, if I have an ideal gas, so I still have the Gibbs relations. So, I have TdS is du plus PdV. For an ideal gas, I can write again du as Cv dt. So, I can write ds as Cv by T dt plus P by T dV. So, I can write this. In addition, for an ideal gas, I have PV is equal to RT, which is my ideal gas equation of state. So, this implies P by T is R by V, which is what I get. So, I can substitute this over here. So, I have this expression and I can now integrate this. I have delta S, my delta and S are looking too similar. Okay, I have delta S. In order to integrate this, I need to know whether Cv is a constant or a function of temperature, because we said for an ideal gas it is either a constant or a function of temperature. If I assume it is a perfect gas, then Cv is constant. So, anyway, the general thing would be that I take this as integral of Cv dt by T, R is a constant anyway. So, R into integral of dV by V. So, I would have to integrate this. In the particular case where I take Cv as constant, I can take Cv out. So, for example, I can call it some Cv naught, it's constant, and integral of this is essentially ln T2 by T1. Integral of this, even when this is not a constant, would be ln V2 by V1. So, I have S2 minus S1 is some expression of this form. I got this expression using this equation. I could have also used the other expression, which was essentially TdS is equal to dH minus VdP. So, I could have done this in a similar fashion. So, this gives me TdS is dH for a ideal gas is Cp dt minus VdP. If I divide by temperature, I get ds is this. From the ideal gas equation of state, I see V by T is R by P. So, I could write this as ds is equal to Cp dt by T minus R dP by P, and I can integrate this. R is a constant, I can take R out. If Cp is varying as a function of temperature, I need to know the variation so that I can integrate it. I will assume for the time being that Cp, that not only is this an ideal gas, but it is a perfect gas, which means Cp is constant. So, for that perfect gas where Cp is constant, I have S2 minus S1, which is essentially delta S, is some Cp naught times ln T2 by T1 minus R times ln P2 by P1, both of which are expressions I can use to find out the change in entropy for an ideal gas undergoing a process, and both these values should be the same for the same process. This also is an interesting thing to look at. So, we have been so far looking at work in the context of the first law, and we said that del W, where we have like a piston cylinder arrangement, is for example PdV, or del small w is Pd small v, and because this is the case, we have been generally drawing PV diagrams, because in this case what we see is PdV is like some y dx is essentially the area under the curve with respect to the v axis on a PV diagram. So, we have been looking at quasi-static equilibrium processes and so on, which are essentially and frictionless processes, which are essentially reversible processes. And in those processes, what we are saying is that for finding out the amount of work done, we can plot the curve and look at the area under it on the v axis, and then find out what is the amount of work done. Now, in the context of the second law and Clausius inequality, what we see is that for a reversible process, we said ds is del q by T, or d small s is essentially del small q divided by T. So, in the same way in which we are looking at PV diagrams here, we can now look at T versus S diagrams. So, if I plot temperature versus entropy, if I have some process which is reversible, then I can plot this. I can only do this for reversible processes, because for irreversible processes I do not know the variation of temperature and entropy. For a reversible process I can plot this. Then for a reversible process I see that del q reversible is T ds. This is like y dx. So, that is like this. So, this essentially would give me this area. So, what we see is that if I plot TS diagrams, temperature entropy diagrams, then for reversible processes, the area under the curve with respect to the x axis or the entropy axis essentially gives me the heat transferred. So, in the PV diagram, the area under the x axis or the v axis gives me the work done, whereas in a TS diagram it gives me the heat transfer. So, therefore, it is quite useful to draw these diagrams because they help us visualize what is the amount of heat transferred and so on. So, I am going to stop here for the moment and continue later.